Okay. Because you can't write on the screen, and then it's not recording. You actually have to write within a program for it to record. But if I use Microsoft PowerPoint to write on, it immediately crashes. And we've seen that a couple times. So we're going to go back to this ancient, simple piece of technology called Microsoft Paint.
You have one.
What's that?
You have one now. One note.
I probably have one note somewhere, but I'm very familiar with Microsoft Paint. I know how to change colors, everything, and it really, I mean, it's got everything you need, doesn't it? I mean, doesn't that look beautiful?
Yeah.
It does exactly what we need. So let's start off with the puns, the basics of acids and bases, and then move forward. So let's say that I threw a couple of softball AP chemistry questions at you, all right? Like research level AP chemistry, research chemistry questions at you. Like, okay, Evelina dissolves 20 grams of sodium hydroxide. Oh, that looks beautiful. 20 grams of sodium hydroxide into 4 liters of water. What's the molarity of NaOH and the pH? So we have 2 aspects to this. The first part is what's the molarity? How do we calculate molarity? Might find AP chemistry students who took the AP Chem exam yesterday. Molarity is moles divided by liters. I picked this 20 on purpose because the molar mass of NaOH is 40. What is 20 divided by 40? Yeah. So we have half a mole of NaOH, and then we're going to divide that by 4 to get it into molarity. What is it? Like 0.8.
Yeah, 0.125.
0.125. We have 0.125 molar NaOH. All right, so we've done this part. Check. Now we have to find the pH, but they've given us something that's hydroxide, haven't they? If I take the negative log of 0.125, I'm going to be calculating a POH. Okay, that's a crazy H. I get a calculator.
About 1.
It's really close to 1. Yeah, it's 0.9. And how do I switch POH into pH?
14 minus POH.
14 minus POH. So our pH is equal to 13.097. I should have done that in the calculator. Wow, why do I need to when I'm perfect? So, cool. Does it sound like a research chemistry level pH, POH question? Okay, so look for a couple of those, just simple switcheroos. Same idea on that similar level. You have a pH of 4.02. You know, what's the molarity of hydrogen in this solution? How do we change pH back into molarity?
10 to the power of whatever your pH is.
10 to the negative 4.02. We are supposed to simplify that also. We're not just supposed to leave it as 10 to the negative 4.02.
So would it be 1 over 10 to the 4.02?
No, like a calculator.
Oh, yeah.
I had a kid once leave that as their answer. That's what I'm saying. Yeah. So 9.54 times 10 to the minus 5.
We don't round up to 9.55.
Sure. Okay. So those were the math kind of basics from acids and bases, the research chemistry edition. Feel like we should do a couple of those questions on the physical test where you're changing masses into moles. And so you're still showing that you have this knowledge of acids and bases. Does that make sense? And of course, you get the equation sheet and calculator. If you want to do it without a calculator, I will give you bonus points. Because you're overdoing logarithms. I mean, I don't think I could do. I could get this 5, but I wouldn't be sure what to do on that side. All right, let's erase all that. I'm fine. Update fail. No. What are we gonna do? All right. What else? Let's get to the weak acid stuff a little bit. We're gonna pick everyone's favorite weak acid. Right? That's the generic weak acid. It reacts with water, and it makes H3O, and it makes A. All right. And let's pick a starting molarity. We'll let the voice of Amanda Montgomery the first give us a starting molarity for choosing. 2. All right. So 2 molar. So with you guys, the X value could be told a couple of different ways. X could be given X hence. X hence. They could give you the pH, right? They could give you a percent dissociation. Those are the 2 more common ways for hinting at what the heck X is. Which one do we want to attack first, a pH or a percent dissociation?
Let's do percent dissociation.
All right. Percent dissociations are always going to be less than 5% for weak acids, otherwise it gets too complex. So let's just pretend that it is, for this one, in a word problem, they say that it has a 2% dissociation. That means X is 2% of the molarity. What's 2% of 2? 0.04. So X is equal to 0.04, which means this is 1.96, which is practically still 2. And then this is 0.04, and this is 0.04. And this feels like they're asking for the Ka then. How would we calculate the Ka? It would be 0.04 squared, basically over 2. I'll write 1.96 because that'll make everybody happier. Right? And then we have a Ka. Basically.
I have no idea what I was going to ask.
Okay, so it's definitely your question. So you have it. We have this like pause right before you can ask the question. All right. So that is a pretty common way of us getting to a Ka to give us a percent dissociation, and we use that for X. Para juntas estudiantes aqui. Questions up here? All right, let's do this again, but this time we will do a pH. So this time they tell us the pH, and I have to have a real pH. So they tell us that the pH is 1.70. to give us the pH of 1.70, that can help us with this value right here. Right? And this value is the amount of hydrogen that was given off. And so we could say the amount of hydrogen is equal to 10 to the negative 1.70. And so we can get, using the anti-log, that this is 0.019995 or 2. So the value for x is 0.02. So the value for subtracting x is 0.02, which means this is 1.98 this time. And this is also 0.02. And so we do 0.02 squared divided by 1.98 to calculate our Ka. And we get a Ka of 2.02 times 10 to the minus 4th. Those are the two common questions where we have to calculate Ka. They give us a percent dissociation, or they give us a pH. Okay, what about OKB?
Just like divide, like calculating 14.
Oh, you're talking about KB? I was just joking. I'm not for that yet. All right, and for our last trick, it's where they give us a Ka, and we have to solve for the equilibrium values. So in this case, we know that Ka can be equal to x times x over 2 minus x. And we are going to assume that Ka is less than 5%. I mean that x is less than 5%. Otherwise, it doesn't work. So we look at the question, and it tells us that Ka is equal to, let's say, 1.8 times 10 to the minus 5th. But we're going to assume that this value for x is small enough that it makes almost no change when you do 2 minus x. 1.98 is not too different from 2. So we're going to assume that value for x is small enough that we can ignore it. And then to solve for the quantities in equilibrium, we cross multiply and take the square root. 2 times 1.8 e minus 5th. And then that's not how you take a square root. And so I got x, what am I writing in yellow? I got x is equal to 0.006. And darn it, that is pretty freaking small.
Yeah. Is the reason for the less than 5%, is that the, like if you round up to a single place, it would still be the same?
Well, a lot of times this number that Amanda gave us would be like 2.00. We're admitting that that's the estimate, right? It's a 5% of 2 is typically less than 5% of 2 is within the estimate.
Yeah.
So as long as it's within the estimate, we don't really know that value is 0. Do an estimate of 0. So what's something minus an estimate? Something, still an estimate, right? And so since we're subtracting in the estimate range where we don't really know that it's impacting the value. And then quite often, now that we've got x, we've got that, we could find the pH. That's usually the last question here, is find the pH. So if we take the negative log of that number we just got, we would have our pH or our pH. Negative log of 0.006. 2.2. Our pH is 2.2. Hey, Solomon. Everyone at home, say hi to Solomon. Or Solomon, say hi to everyone at home. Oh, just feel like drop the voice in the. So what we're doing, Solomon, is we're going through various acid-base scenarios that will appear on an eventual test. So you guys could watch through it and know exactly what type of questions you have. Okay. We started off with real basic, like you dissolve this much into water. What's the molarity? And then what's the pH? Now we moved on to the three Ka issues. Since we've done the three Ka issues, what should we do after that? Is that KB? We should do a KB. So I did a KB demonstration in academic chemistry yesterday. They didn't really know what the hell was going on. That doesn't stop me.
I think about it.
Did somebody look up the KB for carbonate? For carbonate? KB for carbonate. Well, do it as a demo as we also explain it.
2.1 times 10 to the negative
I say that slow. 2.1
times 10 to the negative 4.
just 10 to the negative 4.
Yes.
That is the KB for carbonate. Right? What you said?
Mhm.
Okay. Oh, that's not doing what I thought it was. So what I'm going to do is I'm going to put sodium carbonate into water, and this is a solid. With sodium, is sodium carbonate soluble in water? It's got sodium in it. So yeah. And so we're going to have sodium ions in the water. We're going to have carbonate ions in the water. Oops. Nice. I don't know why I wrote water. Anyway, so we're going to have 2 sodium ions in the water and carbonate in the water. And carbonate will actually react with the water because it acts like a weak base. Right? It acts like a weak base. And so what's it going to do to the water when it reacts with the water? It's a base. What's it going to take from the water? A hydrogen. It's going to take a hydrogen from the water, and it's going to leave hydroxide. And so we could weigh out precisely. But before we do that, let's put an indicator in. I've got some universal indicator. I think you guys have used this stuff before, the like tape, where you pull a bunch out, tear it off, and stick it down into a solution, and then go, oh, it's yellow. That's a 6, right? This pH paper actually just has universal indicator on it. So we're going to take the universal indicator and pour some in there, and then swirl. And this actually shows up as a 7. It's green neutral, which makes sense because right now it's water. It's tap water. I didn't waste perfectly good distilled water on it. But then we're going to add some sodium carbonate, which is a white powder. Doesn't really look like salt or sugar because it's kind of a funky looking powder. And it should react, and that carbonate should steal hydrogens from the water and make, now it's purple. Purple's like a 13 or a 14. So it's a pretty big change. And it looks almost black. And then yesterday I was taking this strong acid. I got sulfuric acid here, like you do. Adding some, and then swirling. and kicked it over to the other side. Right? Now it's like a 1. And you kind of go back and forth. And everyone seems to like color changes. Most of our chemistry life has been boring. There's a nice swirl of colors. Oh, yeah. That's very satisfying. You see how it's like little bubbles? So when acids and carbonates make carbon dioxide, there's actually a reaction occurring between the carbonate and the acid that it can't quite decide what to do. But we got purple here, we got green and yellow in the middle here. Oh, it looks like the carbonate won. The carbonate won in the sense that it's the excess reactant. I don't like that, so more acid. See, we'll just slowly add acid. Doing a kind of lame titration here. What's my gold color, do you think? Oh, that's pretty good. Getting close.
That's green for me. That's not green.
Good enough? Good enough for the thing?
Is it?
Yeah, it's gotta be within 3 of 7 to go down the sink. So it could be a 10. It still go down the sink. You just throw water behind it. So what's going on there is our carbonate is reacting with the water and freeing up hydroxide. Now, the indicator breaks at 14, right? Like it stops being useful at 14. It doesn't go beyond purple. Let's just pretend that we swirled it and afterwards we were like, that thing is a 13. Okay. Oh wait, I was about to write a really complex question. Hell, forget that. No, we're not doing that. I almost waited way too hard to off. I almost was like, well, the pH is 13 and the pOH is 1, and then this would be like a 0.1, and then we could solve for the amount of solid that was put in. Man, over a son of a gun. Is it that hard? Yeah. P minus X, P minus X. This should also be 0.1. This would be, let's call this Y. Y minus X, and we can assume that X is so small that this is still Y. You got it? So therefore, well, it's not that hard. 2.1 times 10 to the minus 4th would be equal to 0.1 times 0.1 over Y minus less than 5%. So we ignore that. So we just cross multiply and solve for Y, don't we? Can't do that in my head. But that's a good thing. 0.1 squared divided by 2.1 times 10 to the minus 4th. I got 48. 48 feel right to anyone in here?
Yeah.
Huh. 48 seems like a pretty high molarity.
I got 4.7.
I like that a lot better. Did you square the 0.1?
Yeah.
Did you get 47.6?
Yeah. We got
It was 10 to the minus 4.
Yeah.
Did you?
I got
I have to pick between Josh and Olaf, and then I'm picking Josh and Olaf.
Because like, if you solve it for y, right, so you shift between solve for y and negative.
47 or 48, it just doesn't make any sense. That's way too high of a polarity. Do you agree? Okay. What'd you do?
I just put it as a calculator.
Oh,
0.1 times 0.1 over 2.1 times 10 to the negative 4.
did you put this in first, please?
Yeah.
But how's that any different than what I did?
Double check.
Well, it's technically the minus 1. Do this. Sorry. It was a scientific notation. The first time I've ever called you anyone a doofus the entire year. Okay. I don't quite know why that answers what that is. That's flabbergasting me. But anyway, yeah, that might be the case. It might be 0.1. Even then, it doesn't. The value can't be bigger than 0.1. I don't know. Let's try it from the regular way. Okay. So the regular way would be like you figure out how much solid you dissolved into there, and then you know the molarity. And let's say that this is like 0.04 molar, which seems like a very reasonable number. Right? And so you subtract some amount, you gain some amount, you gain some amount. And so then 2.1 times 10 to the minus 4 should equal x squared over 0.04 minus x. And hopefully the x value is small enough that we can ignore its existence. We're going to take a square root, not divide. Take the square root. It's not quite small enough. I don't think that's less than. Yeah, that's just barely over 5%. So technically, we're not allowed to do that. Okay, we're gonna do it, but technically, we're not allowed to do that. This is just barely more than 5% dissociation. So we're gonna take that value, plug it back into here. What would we be calculating when we take the negative log of 0.0029? We take the negative log of 0.0029, we're going to be finding out POH, because that's hydroxide. We're going to have POH of 1.13, which means our pH is 12.86. So I kind of like the idea that you can add a solid to water and create a basic solution, because that is a pretty strong conjugate base. Not a strong conjugate base, but a pretty strong conjugate base. All right, how do you feel about those questions, the KBs? Yeah, no.
I have a related question. Like based on like the Lewis structure of an acid, how do you know which hydrogen will participate in this association if it's multiple hydrogen?
Like
But
in
let's
this,
say hypothetically on an exam, they gave you lactic acid and Lewis structure, and hypothetically you asked which hydrogen would participate in this reaction.
what's the formula for lactic acid?
C3H6O2.
O2?
Okay.
Is it 3 carbons in a row or are they in a circle?
Yeah, 3 carbons in a row. And then a hydrogen on the left carbon. Yes, 3 nitrogen here.
3?
Yeah. And then hydrogen. And then there's the second one, there's an oxygen below. And then, yeah. But there's one hydrogen, like, making the chain longer. So from the left, there's C on the right. You know, like the oxygen is from the C. Like,
Wait, why don't you just come up here and draw it?
I think
There's not.
long.
Well, that's what I just got drawn.
Yeah.
Oh, yeah, you should.
It would probably be this hydrogen or this hydrogen. I'm not sure which one.
I said that.
Okay, you know when you point and you go, it's that student over there. I don't know who the hell. The right one? Okay.
Wait, so if you did the bottom one, it's also right?
I don't know.
I first I started looking at formal charge, but it was 0 for everything.
It's not one of these 4.
Yeah, half of hydrogen. There's one OH.
Yeah.
But the right one sticks out.
I like this one better because of the oxygen that's opposite of it.
That's so strange.
I don't know why anyone would care about this question though, because I don't like it.
It's the first
The
question.
circle one.
It was the first question of the
Yeah.
response.
Can't quite talk about that tomorrow.
Why until tomorrow?
What is the question?
Um,
I don't know why they want us to wait.
So this question released tomorrow,
Mhm.
but our school's going to release till
July
July
6th or something like that.
That's so lame.
Well,
You can't.
You got to get all those teachers together to grade them. Usually means the school year has to be over.
But then also like for college stuff, like you have to like take the what's it called, placement tests.
Mhm.
Like it's before that if you want to do it like digitally. So
I know.
I'll also say hypothetically they're in the titration curve, and then it's between a weak acid and a strong, strong base.
Well, we can go over that right now because I was about to do titrations.
And then the midpoint would be where the pKa equals the
And the
pH.
midpoint would be 8 milliliters down there. They get the pKa at like 8 milliliters a day. I know they're like that halfway point.
So we have a titration curve coming at us. Ooh, look how straight I drew that line.
No.
That's so good.
I feel like though.
Did you say strong acid or
We got the weak acid, strong base.
weak acid, strong base? So we have pH here, obviously 0, 14, and there we go, 7. And then along this line, we have the volume of base that's being added, probably sodium hydroxide. And then our curve, I'm going to draw 2 different curves. In red, I'm doing strong acid versus weak. Versus strong base. And then in purple, we're going to do weak acid versus strong base. Notice at the beginning, we have a funny curve, then we have this slow increase. Oh! Okay. So we have 2 very different graphs here if you compare the beginnings. in both scenarios, we're gonna say that the acid, ooh, brown, okay. It is reacting with the base. Just a second. And making water and making some sort of salt. Okay. And in both scenarios, the acid is the same concentration. It doesn't matter if it's a strong acid or a weak acid, they're both the same concentration. And this is the volume of the equivalence point. Is there a hypothetical number you would like to plug into the volume of the equivalence point? 8? 8. So 8 milliliters is the volume of our hypothetical equivalence point. And for the strong acid, we're going to see the equivalence point occur at a pH of 7. For the strong acid, strong base, the pH equivalence point is going to be at 7. And so real easily, we could say 8 milliliters times the molarity of our base should equal the molarity of our acid times the volume of our acid at that equivalence point. Cool. Weak acids have some unique properties. First of all, the equivalence point is between that region there. You find the middle of that region there. The middle of that region there appears to be about there. Is that at 7? That's like 10. I'll take 10. So it appears to be the equivalence point is about 10. And the reason it's at 10 is because the weak acid and the strong base are equivalent, all right? You have done 0.2 molar of both of them. So you subtract 0.2 and you subtract 0.2, and there's 0 of this and 0 of this left over. There's neither acid nor base left over from the initial reaction. But while this reaction is occurring, there's a conjugate being made from the acid that is a decent base, which is going to elevate the pH and make it slightly basic, all right? Because this is a weak acid, its conjugate actually has some power, and it raises up the pH a bit. That's why you don't see the equivalence point at 7 for weak acids. You see it a little bit elevated because of the conjugate. The other fun issue is at the half equivalence point, which would be 4. Do you agree that that's halfway to the equivalence point? There's a fancy point here, which we went over when we did the notes, but that was a while ago. What's that appear to be hypothetically? 4? So at this point, the pH is equal to the pKa. At halfway to the equivalence point, the pH and the pKa are equal. That is only true for weak acid. That's why we're doing that part of purple, all right? Strong acids, what's the Ka for strong acid? Say again? It's maximized. It goes all the way, so it's practically infinity. So you can't really pull a Ka off of here. Why does that work at the half equivalence point? Because you have an equal amount of H and its conjugate both present in there. You've used up half of the acid, and you're halfway there, and you've made the conjugate base, and the pH and the pKa are equal. You can pull that point off. If you know the pKa, can you calculate the Ka? How do you undo a P? 10 to the negative pKa will tell you the Ka. All right, we're gonna leave that there because that has got like all of the titration acid with a strong base stuff. Let's not titrate with a weak base. That's a bad choice. Let's not put a weak base in because then you have like a curve from the weak acid and you have a curve from the weak base, and they kind of merge into some weird math equation I can't have. These are actually math equations. Isn't that kind of like from here to here? What's it kind of look like? From this point to that point, what's it kind of look like? Like a y cubed graph? A y squared? What's this graph? What do you call that?
Cube.
The cube?
Yeah, come up on number 3.
Yeah, I don't quite remember what it's called, but at some point in math you learn like, hey, there is a line, it hits, and then it changes. Each line kind of has its own equation. And you kind of realize, okay, up until we hit this point, it's one equation, and then it changes. You see that happen here, like, and then it changes to a different math problem, doesn't it? Because what's dominating it in the beginning is the weak acid. What's dominating it after the equivalence point is the strong base. So it's the math equation switches. So I kind of like that. The dirty math hiding in there. Cool? All right. Yeah, I'm still doing that. Yeah.
What is a pipette?
What is a pipette?
Okay, right. No. No. Okay. So I got that wrong.
What did you do?
This is a graduated
No,
cylinder.
no. It was, I said, stir it with the pipette. That's what I wrote down. It doesn't matter. It's only
We didn't have a stirring rod.
They didn't.
No.
No.
They already started at the 30.
Yeah, but just in case, stir it again. Shut up, Carson.
I don't know what they're talking about.
I hope you get it too.
Okay. One last scenario, and that is the titration, but with a base. So we'll start off again with our titration curve. Ooh, nice line. And then we'll start off with the strong base, and you're adding a strong acid. And oh, oh, that broke the thing. Okay, I gotta fix that. Strong base, strong acid. Here we go. Pretty much looks like the strong acid versus strong base, but it's been flipped upside down, doesn't it? And then we'll do the weak base versus strong acid. There we go. So what is slightly evil about these questions is it's still a pH they're giving you, when really you wish it was a pOH. So I have seen kids take this scale and flip it and just write the numbers backwards and go 0, 1, 2, 3, 4, 5, 6, 7, you know, all the way to 14. That way, when they pull a value off of here, right, that's where the pOH should equal the pKb. But this is a pH on the graph, and you really need a pOH, right? So they'll sometimes rewrite the numbers on the y-axis for pOH, and then it's more useful. Again, the equilibrium point should be below 7 with a weak base, weak strong acid. Oh, I find it. Okay. But it's all the same info as the last graph, just flipped over to get that extra little fun bit. Okay. I think that's all the stuff from acids and bases. Let me hunt into the notes. That's good enough. All right. Should we call it there? Got plenty of complex acid base stuff. Let's see. Is there anyone we want to say hi to that's not here today? Destiny, who do you want to say hi to?
Lucy and Jordan.
Lucy and Jordan. Destiny says hi. Lucy and Jordan. We both got the shout out. Anybody else? Mondi wants to say hi to Evelina. She's in the room, but she just doesn't want to talk to her directly. Ethan Carson wants to say hi. He specifically said he wants to say hi to you. He misses you. He feels insecure because you're not here. All right. So this has all the stuff in it you need to know for your test. Make sure that you take time